we don't have the table today. I'm going to try to write while standing. So we'll see how that works. Okay. Okay. So let me go over what we have covered so far in chapter 25. We said any two conducting plates can serve as a capacitor. So a capacitor symbol is following. Okay. So if the capacitance is C, we said that the charge that accumulates is Q and minus Q on the if we establish a potential difference delta V across the capacitor, then these are related by Q is equal to C delta V. Okay. We also determined that the capacitance of a parallel plate capacitor with area A and distance D is C epsilon 0 A over D. Okay. We also did the equation for spherical and cylindrical capacitors. I don't remember those, don't memorize them, but you can always derive them. Okay. Then we also did capacitors in series and in parallel, and we said if we have capacitors that are connected in parallel, like C1 and C2, okay, we said that the voltage delta V across them is the same. We said para V, That means parallel capacitors, they have the same potential difference across them, so delta V is the same. Okay, and we also determined that the equivalent capacitance, C equivalent, is just equal to the sum of C1 plus C2. And if we have more capacitors, that will be at C3, C4, and so on. Okay, then we did series capacitors, or capacitors connected in series, like this one, for example. So we have C1 and C2, and we have delta V here. Okay. And in this case, we remember series Q, meaning capacitors in series, they have the same charge. So this is for example Q and minus Q. This is also going to be Q and minus Q. So same charge. Okay. Para V, the same potential difference, but it's also equal to the potential difference across the equivalent capacitance. Okay. Now, if we do the equivalent, C equivalent for a series of capacitors, we said 1 over C equivalent is equal 1 over C1 plus 1 over C2, and so on. If you have more capacitors, you can keep adding. Okay, and we deduced that C equivalent is just equal to the product divided by the sum, C1 C2 divided by C1 plus C2. And we solved a couple of problems where we calculated the equivalent capacitance, and we calculated also, we said if you get the equivalent capacitance, you can work backwards to determine the charge and the potential difference across every capacitor in the circuit. So you start with C equivalent. What is its charge? What is its potential difference? Go backwards, the previous step, determine the charge is the potential difference, and keep going backwards until you can find the charge and the potential difference across any capacitor in the circuit. Okay, so this is where we stopped last time. Okay, today I'd like to go over this example. This is an important example. So what do we have here? We have capacitor C1 and C2. Originally, capacitor C1 is connected to a battery. In this case, it's 6.5 volts battery. So it's charged. It's charged to a charged Q0, or let's call it Q1 initial. Okay. Then what we do, we open the switch. This switch, which is between the battery and capacitor C1. So now capacitor C1 is charged and has the same potential difference as the battery, 6.5 volts. But then we close this switch. So now capacitor C1 and C2 are connected and together, and we want to define what is the potential difference, V final, and what is the charge, Q1 final and Q2 final. So originally there was a charge Q1 initial and there was no charge on capacitor C2. But then when we disconnect the battery and we connect the capacitors together, the charge will redistribute and we will have charge Q1 final and Q2 final in this. So the first step in solving this problem is, first of all, find what is the charge that is initially accumulated on C1. So let's see Q0. We have an equation which says it's C1 delta V initial. Delta V initial is 6.5 volts. Okay, so this is going to be 3.55 10 to the minus 6 farads times 6.5 volts. Let me get the numbers. It's okay, let's solve that. All right. So now we disconnect the capacitor from the battery and then we connect to the other capacitor. When will the charge, the initial charge Q0, if we take the two capacitors after closing the switch, what is the total charge on the two capacitors? The total charge. Will it vary? The total charge is going to be the same because these two capacitors now, they are not connected to anything else. So the original charge that was on the first capacitor, it will redistribute, but still if you add Q1 final and Q2 final, it will be still the same as the initial charge because we said the charge is conserved, it has nowhere to go. So we can say Q1 final plus Q2 final has to be equal to Q0, which is Q1 initial. The charge, this has to do with conservation of charge. Okay, so now we can write what is Q1 final. Q1 final is, we can write, this is C1 times delta V final. Okay, Q2 final is C2 plus delta V final, because that's the potential difference. This is the potential difference that we have. This is equal to Q1 initial, and we said Q1 initial is C1 times delta V initial. So we can factorize delta V final, and we can find, okay, so the pen start writing. So let me just quickly. Okay, so you can see that V final. Let me unplug this quickly and save. And unfortunately, the only way to do this is to disconnect everything or to turn off my computer, close all tabs, and yes, okay, and you can never rely on the technology. Stop. Q1 initial was C1 delta V initial, okay. Then we said Q1 final plus Q2 final is equal to Q1 initial because of the conservation of charge, and we said this is C1 C1 delta V final plus C2 delta V final, and Q1 is C1 delta V initial, and we obtain delta V final is just equal C1 divided by C1 plus C2 delta V initial. Okay, and when you plug the numbers, you find that this is 1.85 volts. 1.85 volts. Okay, now that we have the potential difference in the final configuration, we can determine how much is a charge on each one. So Q1 final is equal to C1 delta V final. Okay, and you find that 6.55 10 to the minus 6 or micro coulombs, and Q2 final is C2 delta V final, and this is going to be 16.5 micro coulombs. Okay, so you have to do it step by step, so if you have conservation of a charge, you have to apply conservation of charge. If in this case there is conservation of charge, the battery is not connected anymore. Okay, let's proceed. So this is the example that we just have done. All right, let me go to the presentation mode for the next part. It's taking too long here. Okay, so if we have the capacitor not connected to the battery, no charge is on the capacitor, okay? And we said if we connect it to the battery, it will charge to a charge Q, and the potential will be established across the capacitor, which is going to be equal to the potential from the battery, okay? The battery actually does work to transfer electrons from one plate to another. So there is chemical work that is converted into electrical work. And the work required to charge the capacitor is stored in a form of electric potential energy in the capacitor. Okay? And after we disconnect the battery, we have a charged capacitor. So we have a potential energy stored, potential electric energy. And so you can recover this energy that is stored in the capacitor by discharging it through a circuit. For example, if we connect a device, for example, a flashlight, the capacitor will discharge through this flashlight, and you will see the flash. And so this is how we often use capacitors. Okay? We want to determine the electric potential energy. So we want to determine U, electric potential energy that is stored in a capacitor, and the way we're going to do it, okay, so this is the equation. We have to try to see how we can get this equation. So it's equal to Q squared divided by 2C, and since Q is equal C delta V, Q is equal C delta V, we can also, so we can write this as 1/2 of C delta V squared, and we can also write it as 1/2 of Q delta V. So we have three equations we can use for the electric potential energy of a capacitor. So if you have the charge and the capacitance, you can use that. If you have the capacitance and the potential difference, you can use that equation. But if you don't have the capacitance but you have the charge and the potential difference, you can use this equation to determine the electric potential energy. Okay, let me skip the demo because we lost some time earlier. Okay, so here, if you plot the delta V versus the charge, remember we have Q is equal C delta V. So delta V is equal 1/C times Q. So it's actually a straight line with a slope 1/C. So this slope here is 1/C. Okay. And if we think about the work that is done by the battery to add, let's say, dq prime, a small element, let's say dq prime here, okay, to the capacitor, it will have to do some work. And the work, remember, we said work, potential energy is equal delta V times Q. So here, since it's an element charge dq prime, we can multiply delta V prime times delta Q prime. We want to determine how much energy is needed in order to charge the capacitor from zero. It starts from zero charge till it reaches the maximum charge of Q, or capital Q here. Okay, so what we do the integral, we sum all of these elements. So this is actually, this energy here is delta V times dq prime. So this is equal to this. What we can do, we can add all of these elements. So it's a Riemann sum, or we can just do the integral. We can do the integration. Okay, so the total work is the integral of okay, we replace delta V prime by Q prime divided by C. This is due to the equation of the capacitor. Q is equal to C delta V. The work required is now we can integrate from 0 to Q q prime over c dq prime. So the integral of x is 1/2 of x squared. So 1/2 of q squared divided by c. And if we evaluate it between 0 and q, this is what you end up. This is q squared over 2c. Since q is equal to c delta v, you can also write it 1/2 of c delta v squared, or you can write it also 1/2 of c, 1/2 of q delta v. Okay, so this is the proof of the equation, of this equation here, of the potential energy that is stored, potential electric energy stored in a capacitor is q squared over 2c. Okay, let's try to determine the energy density. Energy density is energy per unit volume. So we divide the electric potential energy that we have stored in the capacitor divided by the volume of the capacitor, and we can determine the volume if we have the area and the separation. That's the area times d. Okay, and when we do that, you will see that we get the following equation. The energy density, and for energy density we use small letter u, not capital letter. I don't know, they should have used something else, but so it's equal to the total potential energy divided by the volume. Okay, and when you do that, you find that the for an electric field that exists in any point in space that has electric potential energy U, it's given by this equation. It's 1/2 epsilon 0 times the magnitude of the electric field squared. 1/2 epsilon 0 E squared. So this is an equation for the energy density. And by the way, does not to have to be in a capacitor. Any electric field in space, if you have an electric field in space and you take a certain volume of space, and let's assume the electric field is uniform in that volume, if you multiply 1/2 epsilon 0 times E squared, it will give you the energy per unit volume for this electric field. So it's not only for parallel plate capacitor or cylindrical capacitor. This is a general equation that you can apply whenever you have an electric field in space. Okay? So let's see the proof for at least the parallel plate capacitors. We know U, we have seen, and the volume, so let's replace them. 1/2 C delta V squared divided by the volume of the capacitor, which is A, the area of one plate times the distance between them. Okay, C is epsilon 0 A over D, and so this simplifies, so we can write, and delta V is just, remember, for a uniform electric field, delta V is equal E times D, or we said the electric field is minus delta V, and we're interested in the magnitude here. Okay, so the A's will cancel, the D's will cancel, and you end up with this equation. You can see the D's will cancel and the A's will cancel in this equation, and you obtain the energy density, or this is the energy per unit volume, is just equal to 1/2 epsilon 0 E squared. We can do this also for cylindrical or spherical capacitor. We will end up with the same equation for energy density. Okay, so this holds true for any electric field. Actually, you don't even have to have a capacitor. Okay, so let's try to do this example here. We did something very similar before, but now we're going to do it much more elaborate. What happens to the potential, the electric field, the stored energy, the energy density for the same charge Q? If we have now a capacitor that has a charge Q, and we increase the separation between the two, we double the separation, so we have D here and 2D here. Okay, we said yesterday, since the capacitor is not connected to anything, the charge is conserved. The charge has nowhere to go, so it will stay at Q and minus Q. Okay, but we want to do the other things. So first of all, let's call this capacitor 1. Let's call this capacitor 2. So what's C1? C1 is epsilon 0 A over D. Okay. What is C2? C2 is epsilon 0. The area is the same, divided by the distance is now 2D. So this is equal to C1 over 2. So clearly the capacitance decreases. That's the first step. Second step, what is the potential? We know there is an equation for potential. We know that Q is equal to C delta V. So let's do delta V1. Delta V1 is Q divided by C1. Okay? And delta V2 for the second capacitor is the same charge, Q. I'm using small q, it's okay. Divided by C2. And we know C2 is C1 over 2. So delta V2 is actually equal to 2 delta V1. So you can see the capacitance decreases, the charge stays the same, the voltage has to increase in order to maintain this equation. Okay? Third step. What is the electric field? We have an electric field is just equal to the potential difference divided by the distance. Okay? So let's drop the minus sign. So this is delta V, delta V divided by D. This is E1. Okay? E2 is going to be delta V2. This is delta V1. Delta V2 divided by the distance is now 2D. Okay? This is 2D. But we already said delta V2 is 2 delta V1. So this is equal to 2 delta V1 divided by 2D. The 2's will cancel and we end up with E2 is equal to E1. Interesting, huh? The electric field did not change even though the separation between the plates doubled. But because the separation doubled, the potential also doubled. And so when you divide the potential by the distance between the plates, you still find the same electric field. So the electric fields are the same. Okay? How about the stored energy? U. Okay? So which equation you would use? I would use 1/2 or Q squared over 2C. 1/2 of Q squared over C. 1/2 Q squared over C. So U1, this is U1 and C1. Okay, U2 is also 1/2 Q squared, the charge is the same, divided by C2. But we said C2 is C1 over 2, so this is U2 is going to be equal to 2 times U1. So the electric field remained the same, but the potential energy stored in the capacitor has doubled. Okay, it has doubled. So it has doubled. Okay. The final thing is, what is the energy density? The energy density U1 is 1/2 epsilon 0 E1 squared. Okay, for the first capacitor. For the second capacitor, potential energy is 1/2 epsilon 0 E2 squared. But E1 and E2 are equal. E1 is equal to E2, and this is what we have found earlier. Okay, so that means the energy per unit volume U1 is equal to U2. Clear? Any of these can be an exam question. You can be given a question and you are asked to determine what happens to the energy density, or what happens to the electric field, or what happens. So here we did what happens to the capacitor, the potential difference, the electric field, the energy, and the potential energy, electric potential energy, and the energy density. Is this clear? Any questions? Okay, next. Okay, so this is what we have done. Okay, now the same problem, except the capacitor is now connected to a battery. So while we are increasing the distance from D to 2D, the capacitor is connected to the battery. The battery will maintain the same potential difference across it. So delta V is going to be the same. So here, this is D, and this is 2D. Okay, but let me call it the delta V. Delta V are going to be the same because the battery maintains them. So let's look at the capacitance. We said C1 is epsilon 0 A over D. C2 is epsilon 0 A over 2D. So C2 is equal C1 over 2. Okay? what happens to the charge? Okay, will the charge change or not? It will change because the potential is the same, capacitance varies, and Q is equal to C delta V, so the charge will have to change. So let's say Q is equal to C1 delta V. Okay, so this is Q1. Q2 is C2 times delta V. The potential is the same, it's maintained by the battery. So let's replace C2. This is C1 over 2 delta V. So you can see Q2 is Q1 over 2. In the previous example, remember, the charge did not change. In this example, because it's connected to a battery, the charge changes. Thank you. Everybody signed? Okay, so what happens to the electric field? E1, okay, we said it's delta V magnitude divided by D, delta V, and delta V is, now E2 is delta V because the potential is still the same, divided by 2D. So you can see the electric field is now 1/2 of the first electric field. Remember in the previous example, I think E1 and E2 were the same. Okay, now it has changed. It has decreased. Okay, how about the energy, the stored energy, U1? Okay, so since I have delta V and I have C, I will use 1/2 C delta V squared. 1/2 C1 delta V squared. Okay, U2 is 1/2 C2 delta V squared, because delta V's are the same, so that's simple. C2 is 1/2 of C1, so U2 is 1/2 of U1. So you can see, in this case, the electric potential energy that is stored is half. I don't know what happened in the previous one. In the previous one, the previous one, it was twice. U2 was twice U1. In this case, U2 is 1/2 of U1. Very different. Okay? All right, so the last thing we're going to do is the energy density. The energy density, U1, is 1/2 epsilon 0 E1 squared. U2 is 1/2 epsilon 0 E2 squared, but E2 is equal E1 over 2, so E1 over 2 squared, that's E1 over 4, so you can see, small U2 is just equal to U1 divided by 4. In the previous case, I think they were the same. They were the same in the previous case. So clearly, there is a difference between a capacitor that is connected to a battery, things very different, in a very different way, because the potential is the same, and a capacitor that is charged and then disconnected from the battery. The things that happen are very different, because the charge in that case is conserved, the potential difference is not conserved. So if I give you this in if you get this in an exam, you should be able to reason it very easily and clearly. Okay, so these are what we have just done. Okay, so let me do this example, and so we have two capacitors, C1 and C2. Capacitor C1 is larger than C2. They are charged to the same potential difference delta V initial. So they are connected to a battery, then disconnected. So let's say the initial battery has a voltage delta V initial. So you charge the two capacitors to the same potential difference. Okay. The charged capacitors are removed from the battery, and their plates are connected with the same polarity as in the top figure. So notice the positive polarity is connected to the positive polarity, the negative polarity is connected to the negative polarity of the two capacitors. Okay, so that's what happens when we close the switch. The question is, after we close switch S1 and S2, find the final potential difference delta V final. Okay, so this is easy. First of all, let's see what happens to each capacitor before they are connected. So initially, we have Q1 initial is equal C1 delta V initial. Okay, Q2 initial is C2 times delta V initial. Okay, now when they are charged and we connect them, okay, so what is the Q final? Q1 final is going to be C1 delta V final, and Q2 final, and this is after we connect them, is C2 delta V final. Now, is the charge conserved in this case or not? Total charge, is it conserved? Yalla jama'a. Yes, it is conserved. So speak up your mind. Okay, it is conserved because these two capacitors, after they are charged and they are connected together, they are not connected to anything else. So the charge, this is a positive charge, let's say 100 coulombs here, and 100 coulombs here, when you connect them together, you have 200 coulombs. So the charge is conserved. So we can say Q1 initial plus Q2 initial is going to be equal to Q1 final plus Q2 final. Correct? Because the charge is conserved in this case. And so let's replace Q1 initial and Q. So we have C1 delta V1 plus C2 delta V2, the V initial is equal C1 delta V final plus C2 delta V final. So notice here we can write this C1 plus C2 delta V initial is equal to C1 plus C2 delta V final. So this cancels and we obtain that delta V final is equal to delta V initial. Clear? And you charge a capacitor, let's say it has a 10 volt potential after you disconnect from the battery. You charge another capacitor, it has 10 volt potential. Then you connect them in parallel, not in series. Then you connect them in parallel. So 10 volt battery, if you connect it in parallel with a 10 volt battery, it still gives you 10 volts. It doesn't give you 20. If you connect them in series, with positive to the negative terminal, it will give you a total of 20. So here, the potential is going to be the same. Find the total energy stored in the capacitor before and after. So here, U1 initial is, we can use any of the equations. So let's use 1/2 of Q1 initial squared divided by C, okay? And U2 initial is also 1/2 Q1 initial, Q2 initial squared divided by C, this is C1 and C2. U2 final, same thing, is 1/2 U1 final. U1 final is final is Q1 final squared divided by C1, and U2 final is 1/2 of Q2 final squared divided by C. If you add them, you will find they are equal. So the total potential energy is U1 initial plus U2 initial. So it's going to be 1/2 of C1 and Q1 initial squared, 1 initial squared plus Q2 initial squared divided by 2 C2, and we find the same thing here. Yes, and we said so the fact that delta V final is equal to delta V initial, that means also Q final and Q initial are equal. So since this is equal to this one, we know Q1 final is equal to Q1 initial, and Q2 final is equal to Q2 initial. So you end up with the same equation. So U final is going to be equal to U initial, and so this is going to be the same equation. Clear? So if you have Abdullah, pay attention please. Okay, so if you have two capacitors and you connect the same polarities, basically this is what you get. Now let's make this more difficult. Okay, and pay attention. This is the most difficult example in this chapter. Okay, so now we're going to do the same thing, except we're going to attach positive polarity to the negative polarity and negative. So this is what we're going to do. So this is the positive polarity and this is the negative polarity of the second capacitor, and that's how we're going to attach them. And the question is still the same. So the opposite polarity. Find the final potential difference delta V final between A and B after the switches are closed. Okay? So the way I'm going to do it is going to be a little bit different from the way in the book. Okay, and I think it makes more sense. Now, let's assume you have 100 coulombs here. Okay, and you have minus 50 coulombs here. Okay, so you charge the two capacitors, one is more than the other. Then you connect them. What happens when you connect the two capacitors? What will be the charge on this side? Let's assume now we have one C equivalent. And this is Q final, and minus Q final here. What do you think the charge will be? Anybody? Nine? Yes. So it's not 150. Because what happens is 50 coulombs will cancel with minus 50 coulombs. So we have extra electrons on one charge and missing electrons on the other plate, and you connect them together. So the 50 and minus 50 they will cancel, but you still have 50 more. So in this case, Q final is actually equal Q1 initial, which is minus Q2 initial. Okay, it's minus Q2 initial, and Q1 initial is 100 coulombs, let's say. And Q2 initially is that's 50 coulombs. Okay, we already have the equation for that. Remember, Q1 initial is C1 delta V initial, and Q2 initial is C2 delta V initial. Okay, so we can say that Q final is Q1 minus Q2, so that's C1 minus C2 times delta V initial. Okay. Now this is the equivalent capacitance. What is the equivalent capacitor when two capacitors are connected? In this case, they are connected in parallel, okay, because they are touching on both sides. Okay, what is the equivalent capacitance? The sum of the capacitance. So I can write C equivalent is actually equal to C1 plus C2. All right. Now, can I determine delta V final, which is the potential across this delta V final? I can. Because I have Q final is equal C equivalent times delta V final. Okay? And I have C equivalent, that's C1 plus C2 times delta V final. And I have Q final, it's equal to C1 minus C2 delta V initial, so this is equal to C1 minus C2 delta V initial, and I can determine delta V final. Delta V final in this case is C1 minus C2 divided by C1 plus C2 delta V initial. واضح؟ So I did it a little bit different from the previous example to show you sometimes you can use different techniques to solve a problem. So I determined the equivalent capacitance. I determined what happens to the charge. Since I know the final charge, I can determine the potential difference, delta V final. Okay? And the next question, find the total energy stored in the capacitor before and after the switches are closed. We can use the same technique as before. So U1 initial is, we can have 1/2 C1 delta V initial squared. U2 initial is 1/2. Oops. What's happening? Huh? What should I do? Yeah, let me try to end the show. Okay, so we lost everything. Okay, anyway, so if you, so notice this is delta V final is C1 minus C2 divided by C1 plus C2 times delta V initial, and we can use the same, the equations for U1 and U1 initial, U initial and U final, because we have everything. We have the charges and we have the potential differences, we can calculate that, and we find that it's different from U initial. In the previous example, we find them to be the same. In this example, notice it's 1/2 C1 minus C2 squared divided by C1 plus C2 times delta V initial squared. One extra question is given here. What happens if C1 is equal to C2? So if C1 is equal to C2, that means if we have 100 microcoulombs here and we have minus 100 microcoulombs here, what will happen when you connect them? They will cancel each other. They will cancel each other. That means you have no more charge stored. The charge is zero. The potential difference is zero. The energy is zero. So if you take two capacitors and you charge them, and then you connect them, you reverse polarity, as if you have done nothing. You lose your charges from the two capacitors. Okay. Okay. So next. All right. This is for the students who are in biomedical engineering. The principle of the charging a capacitor is used for a defibrillator. A defibrillator is a device that is used when somebody has cardiac arrest. They put him and they shock him with the defibrillator in order to re-establish the electric rhythmicity of the heart beat. So usually what they do, they have a very high voltage source, in this case 5,000 volts. They charge a capacitor. This is a 32 microfarad capacitor in this case. Okay. Then they disconnect the battery when they switch from this position to this position, and so they put the two plates on the each side of the heart, one on the right and one on the left side, and then they push a button to close this switch. Okay, and when they do that, the charge that is stored and the energy that is stored in the capacitor will be used to cause an electric shock through the heart muscle, and sometimes that will bring the rhythmicity of the heart back to normal. I'm sure you have seen it in movies and so on. So this is the very important principle in which, or a device in which we use the charging of a capacitor and the storage of energy in a capacitor. Okay, let me do this example, and assume we have a thunder cloud with a width of 2 kilometers and a length of 3 kilometers. Okay, it hovers over an altitude of 0.5 kilometers over a flat area. Assume the cloud and ground form a capacitor plates with a charge of 80 coulombs. So the charge is 80 coulombs. So here, this is the cloud. It has 2 kilometers on this side, 3 kilometers on this side, and I think about it as if it's one of the plates. The ground is the other plate. Okay, and the distance between them is 0.5 kilometer. Okay, and the charge in the cloud stored is 80 coulombs. What is the potential difference between the cloud and the ground? Very simple. We use just we have Q is equal C delta V. So delta V is equal Q divided by C, and Q is 80 coulombs. C is epsilon 0, the area, divided by D. So this is 80 coulombs divided by epsilon 0, 8.85, 10 to the minus 12. Okay, 10 to the minus 12 times the area. The area is 2,000 times 3,000 meters divided by the distance between them, which is 500 meters. Okay, when you do that, you find the result is this is approximately 7.5 10 to the power 8 volts, 7.5 or let's write it 750 million volts. That's the voltage that we have between the cloud and the ground. The next question, okay, the lightning strikes requires an electric field strength of approximately 2.5 million volts, megavolts per meter. Are the conditions described in the problem statement sufficient for lightning strike? So let's look at what is the electric field. Electric field, we said, is delta V over D, the distance D here, okay? So that's 750 10 to the power 6 volts divided by 500 meters, and we get, in this case, 1.5 million volts per meter. This is less than 2.5 million volts per meter, and hence we will not have thunder strike, because it's not enough. The potential difference between the cloud and the ground is not high enough to cause breakdown of the air in between, and hence the lightning strike. If it exceeds that, then we will see that the thundercloud. We get the strike from the thundercloud. What is the total electric potential energy contained in the field? So the total potential energy, we can use any of the equations, 1/2 of C delta V squared. Since I don't have C, I will use the other equation. I will use 1/2 Q delta V, because I have both. And when we calculate that, Q is 80 coulombs and delta V is 7.5 10 to the power 8 volts. We get 2.9 10 to the power 10 joules. That's 290 billion joules. So you can convert that in kilowatt hours, okay, and you can determine probably enough to give energy to the Abu Dhabi for 1 day. If only we can find a way of harnessing the energy from the clouds, that would be a Nobel Prize. Okay? Alright, so I will stop here. Sorry for taking 1 minute longer. Tomorrow we'll solve some problems. We'll finish the last section and we'll solve some problems. So I will see you tomorrow. So please finish the homework for those who did not finish tonight. And I posted already the homework for this chapter. And I want you to finish early this chapter and the next chapter, which is much easier than this one. Because I want you to spend time preparing for the exam by solving old exam problems. Okay?